Good morning, everybody. We are going
Evening.
to be going through the previous exams today. We're going to start with the fall 2020 exam. So, taking a look at page, or I guess problem one, where we're dealing with ranking your acidity, which looks like I got cut off. I'm just going to write it back on there. Rank. From most acidic to least. So, this is going to be all about our pKa's. As a reminder, we've got our most acidic thing that we're going to be dealing with is ketones. Or sorry, our least acidic. There we go. So generally speaking, a ketone should have a pKa of around 19. Aldehyde is going to be slightly more acidic. Next, we're going to start getting into things that have two ketones that are adjacent to each other, or esters. So the diester is going to be a little bit more, or sorry, our least acidic of this kind of trio. And I can talk about why in a second. Versus just having one ester and one ketone is going to give us a pKa of around 11, and then having a diketone is going to be around 9. We also have a carboxylic acid on here, which has a pKa of around 3. So the reason that this is more acidic than this here, all has to do with resonance. So if we take a look at our conjugate base, we can have resonance to both of these positions. But if we take a look at one of these diesters here, they will still have that, but they'll also have something else that's pulling them away from it. A little too far away. So we have resonance to both of these, but so do these oxygens, which is taking a little bit away from our resonance from that acidic position. So it's just going to make them slightly less acidic in this spot. There was a question in the chat as to why an aldehyde is more acidic. Why is your aldehyde more acidic? And it's actually the same concept. It's just hyperconjugation, which we've never really talked about. Um, Hyperconjugation is this concept that you have basically moments where you break carbon-hydrogen bonds very quickly, and they can like slowly you'll have your like, H plus floating off in solution. It's a very odd concept, and it's kind of yet to be proven, so I wouldn't put too much faith in it, but that is kind of the general concept between why an aldehyde is more acidic, because it doesn't have any hyperconjugation on the side with an H on it. Um, but again, that one's more of a theory than anything else at this point, so I wouldn't worry too much about that. So let's take a look at these. I'm going to erase these so we can actually see. What we're dealing with. All right, so taking a minute to assess these. I'm going to kind of number them. So if we take a look at this first one, this looks like our number 3. We've got esters on both sides of it. This is going to give us a pKa of around 13. We've got a carboxylic acid next. That should have a pKa of 3. Next, we have our 5. It's the exact same structure, so that would give us pKa of 9. We've got, it's a diester, but they're spaced differently. Ooh, I didn't actually give you guys pKa for these. This is actually going to be even higher than a ketone. I forget what this is, like 21. Essentially, in order to have these kind of compounding effects, you need to be in between two ketones. If you are two away where you have an sp3 center here, it essentially negates it. Same thing if you had like significantly more space here. Both these sp3 centers are going to negate any sort of effect you had that lowers your pKa. So we treat this just like it's a normal ester. And you're basically only looking at this portion here because there's no resonance through this sp3 center. Eraser, there it is. All right, so ester pKa is going to be a little higher than ketone. It's probably around 21. Lastly, we have what looks like 4. It's just an acyclic version, so that's going to have a pKa of around 11. So putting them in order from most acidic to least acidic is literally just smallest to biggest. So our carboxylic acid should be our most acidic. And then the next biggest number is 9, 11, 13, 21. So if you know your pKas, this is a fairly easy process. I'll give you guys a pKa for a diester. On that chart. Or sorry, single ester. All right, let's move on to the next one. We'll come back and do one of these again when we do the other, the spring exam. We are not going to do NMR again. We'll just do a naming with carboxylic acids. Which we can do, let's do like a little example of that. So all right, taking a look at these. We've got 1, 2, 3, 4 carbons in our longest chain. This is going to be butanoic acid. We've got a fluorine on 2, chloro on 3, doing our RNS. Fluorine is going to be our highest priority. We've got carbon bonded to oxygen, carbon bonded to chlorine. Chlorine is larger, so chlorine will be our second highest. Oxygen will be our third. This is going counterclockwise. Nope, wait. Clockwise, so this should be R. Looking at our other center. Chlorine to be our biggest. Carbon bonded to fluorine, carbon bonded to itself. Going clockwise again, also R. So putting it all together, 2R, 3R. C comes before F, 3 chloro, 2 fluoro, and then butanoic acid. So, bit of a reminder on nomenclature there. Take a look at the next page. All right, so starting to get into some reactions here. Our first one is dealing with this phthalimide here. We've got excess, so we're going to be attacking both of these bromine centers. Oops. On the bromine. I'm not going to draw out that giant compound. From there, our hydrazine can come in to kick out the rest of the skeleton and just give us nitrogens in those positions. So this is going to let us generate a diamine. Where NH2 replaced that Br there. Our next one, we're starting to get into This is a Grignard attacking CO2. So we're going to elongate our system by 1 carbon. So we need a 5-membered ring bonded to a carbon that has 2 bonds of oxygen. Let's see. Okay, so this was our halo form reaction. In NaOH and Br2, it tends to go and brominate as many times as it can. So in our first step, we're going to tribrominate. And then this is a particularly good leaving group. So when we add an H3O plus, this could act like an acid chloride. And give us a carboxylic acid as our main product. All right, so SOCl2 is going to give us an acid chloride. And then the amine can come in and make an amide. That one's pretty straightforward. Let's see, we've got a Claisen condensation next. It's symmetrical. We're going to pull off one of these 2 protons so that we can do a cyclization here. It's going to give us a 1, 2, 3, 4, 5, 6-membered ring. The position we attack from should be carbon 1. The position we close the ring to should be 6. So then 2, 3, 4, and 5 are here. 2 had a methyl to it. 4 had a methyl. Oops, it's like red or black. 2 had a methyl, 4 had a methyl there. Now we're going to close our ketone, kick out this OMe to get our final product. H3O plus and Br2. We didn't talk too much about selectivity on these. If you protonate, water is going to be a small base, so you're more likely to form your enolate, or sorry, enol in this case. On the more substituted position, which can then attack your Br2. To generate your product. We have a Robinson annulation next. We're going to be forming a negative charge here. Doing a Michael addition, which will come back down and protonate. We'll end up generating in our first portion something that looks like this, which can protonate to form a ketone. From here, we'll make a negative charge in this position. Do our cyclization, we're going to make a 6-membered ring. We'll eliminate our water eventually. And then we need 2 methyl groups coming off of here because we had 2 of them over here. All right, we're doing an aldol for our next one. I wrote out assume cross coupling as your major product. So you're assuming it's attacking the other molecule. We have an aldehyde and a ketone, so your aldehyde is more acidic. You're more likely to generate this negative charge here. We would initially make this alcohol, which can be, with heat, condensed in order to make our aldol condensation product. Which is probably going to be Z, or E, not Z. To give us this here. We have a start enamine synthesis next. So we'd make an enamine and then do an addition to a Michael acceptor here. Enamine is a pretty large base, so we're most likely going to generate our negative charge on our left substituted end, which can come in and do an attack. To give us this product here. Lastly, doing another cross coupling. LDA is a large base again, it's going to deprotonate. Left substitute center. Going to generate this aldol product. This page is pretty tough. All right. Give you guys a second, and then we'll go on to the next one. All right, starting to get into some. Yes, the final exam is tomorrow. The class should end. It ends tomorrow. There's nothing on Friday. Today's quiz is over chapter 20 things that we talked about in recitation. So let's take a look at this. synthesis here. We are going to be adding carbons, taking a look at this. I think the way we did it was treating our starting material like it was this here. So if we oxidize it, we could throw in a small base. Methyl iodide. Do an alkylation on our less substituted center. We could do the same thing on our more substituted center with a large base. Give us a general carbon skeleton. And then to get rid of this, a couple of different possibilities. I'm going to go through like the rainy nickel one. H plus and dithiol, followed by rainy nickel. Can get you to your final product. Could have also done this with something like just reducing it, making a double bond, throwing an H2. Or you could have gone through like hydrazine, KOH, things like that. A couple of different options for getting rid of a carbonyl. All right, taking a look at this bottom one here. We've got I think we're going to do one synthesis problem. Well, wait, did I skip the reagents page? We're having a reagents page, I just skipped it. I'll go back to it, sorry about that. Didn't realize I went past it. I think we're actually going to have two synthesis problems on this exam. So you'll have two synthesis, two mechanisms, synthesis, nomenclature, pK, and reagents. So let's do the second synthesis problem. This one is going to be a couple of different ways you could do this one. I'm going to do it through a phthalimide. So if I throw in this phthalimide on here, I can actually leave it on for a little bit. So let's do our next step. So we want to make a 6-membered ring, which would be 1, 2, 3, 4, 5, 6 is we'll replace this Br with a nitrogen. So we need to make a carboxylic acid on the end, probably turn it into a acid chloride. and let it close on its own. So to make our terminal oxygen, we want BH3THF. NaOH, H peroxide here. We could oxidize this with chromic acid. Probably get rid of the phthalimid at this point. And then if you throw in SOCl2, it's going to make that into an acid chloride, and then just close. So it'll get you to your final product. And kind of draw up a little step mechanism for this one. So this kind of deals with thalamus protecting group, which we never really talked about. So when we're too much about that concept, we'll see what the synthesis ones were from the spring exam. All right, let's take a look at the reagents page, which I apparently skipped. Here it is. All right, we need to add this weird looking spiral compound here. So we're gonna need 1, 2, 3, 4, 5 carbons, and then something to attack on it. So let's throw an NaOMe. We need to add a 1, 2, 3, 4, 5 carbons, and then chlorines on the end in order to attack. So we pull off a proton, attack one of these. No, no. We don't actually need this other reagent box here. Throw an NaOMe again. Pull off our other proton, and it'll close. All right, we're making a phthalimid. We need to deprotonate it. You could add an NaOH or KOH, either's fine. We're adding 3 carbons. We need to get rid of the phthalimid. So adding in hydrazine, followed by We're making an amide, so we need an acid chloride. So to make our amine, we can come and kick this out to get to our final product. Let's see, we need to do a Claisen for this one. We've got, see, this would probably fit. There's 3 carbons there, fit onto here. And then we'll need 1, 2, 3, 4 carbons for our what we're attacking. So adding in NaOET. Followed by a 4 carbon. Ester is going to give us the basic skeleton of our final product. From here, you want the ester? Okay. And I'll just completely draw it out. LAH. And water gets us to our last product. So throwing in LAH lets us reduce this all down to alcohols. Oh, this is the one where I need H2. Okay. Question in the chat. How do the oxygens on the side come off on the first problem? Oh, is that a typo? I guess you could add in, I didn't even notice that. We are, thank you, a soft calculating region for these. These esters here turn into aldehydes in this product. You could add in like ethyl cuprate. And I would probably do a soft alkylation for these. Yeah, I didn't even notice that. Yeah, so these are apples in your final product. So in order to change those from esters, someone asked what is the second reagent. They only turn into methyls if you use methyl cuprate. So whatever is in this box is what you'll add. What is the second reagent? But I'm confused by your question. What does the second reagent, not the second box of problem 3, look like? Is it just this one?
So that's the second box look
Yep,
like.
that's sorry, say it again.
That is the second box. It look like Esther, right?
Yep. Yeah, I just drew it out larger. So it's an ethyl ester.
That's totally is just two oxygen.
Yep,
Okay, thank you.
you're welcome. All right, last one. We need to do a Robinson annulation. This is going to give us the majority of our skeleton. To get rid of all of this, probably the easiest thing would be to do is add H2. It's going to reduce it all the way down to alcohols. And then to replace those alcohols with bromines, you could add in PBr3. Similar to adding SOCl2 with a alcohol. Or double bonds now. That's the wrong spot. All right, let's look at the mechanism phase, take a break, and then take a look at the other exam. I feel like this exam was a lot harder than the spring one. Yeah, this is hard mechanism. All right, this is gonna be a lot of steps. These are like the two hardest mechanisms in the class. So let's pick up the H. Whoop, not that. Pick up the H. Water can attack. Let's do a proton transfer. This has another resonance structure we can draw. From here, we've made our protonated amide. This can yet again get attacked by water. Do another proton transfer. Kick out the amide. And then lose that H plus. To get to our final product. All right, doing a Robinson annihilation. We are going to pull off our proton. Attack our Michael acceptor. We can reprotonate. I'm going to erase the other one. Give myself more room to do this. Pull off the proton from the terminal position. Which can do an aldol condensation. We're going to form what looks like our main product. I'm going to grab a proton. And then in our final step, we're going to do this double bond formation in order to get to our final product. It feels like a particularly mean exam. Let's take a look at the spring one after this, see how that feels. This definitely seems like it was pretty harsh. All right, let's take let's go till 10:15, come back, take a look at the spring exam, and talk through that one. So, see you guys in about 8 minutes. right, let's start taking a look at the spring one. So we're dealing with the same concept we were before, looking at aldehydes and ketones. We've got an aldehyde here, so it should have a pK of around 17. Got a diketone, should have a pK of 9. Regular ketone here, pK of 19. Ketoester, so part ketone, part ester, should have a pK of 11. And then this is benzoic acid, which is actually pretty low, has a pK of around 1. The other one has acid in the name of it, so you're probably pretty good sign that it's your most acidic. So putting them in order from smallest to biggest, our most acidic would be this benzoic acid, followed by 9, 11, 17, and 19 here. Crossing out the whole NMR page. There's whole NMR page. All right. This reagents page, which is going to start off with the Claisen condensation. Got 1, 2, 3, 4, 5, 6 carbons in between. This might be the exact same problem we did before without the methyl groups on it. We're going to make a 6-numbered ring. Close our ketone, kick out this ethyl group. To make our final product. CN with H3O plus goes back to a carboxylic acid. NaOH is a small base. It's going to do a Claisen with another equivalent of itself. So we'll pull out the proton from a more substituted position. In order to make our Claisen condensation product. All right, we've got an acid chloride and an amide. Nope, and an amine should make an amide. We're assuming the cross-coupling product on our next one. So we're going to be pulling off the proton here. Doing a nucleophilic attack. We're going to pull it off from our aldehyde because that's the more acidic one than our ketone. Might redraw this in a different way. There we go. And we're going to form our aldol product here. All right, right, we've got another acid chloride and a carboxylic acid here. As well as make an anhydride. LAH reduces amines and enamines down to just amines. We've got our alkylation. We've got a small base next. So we can pull off our more substituted proton. Means that's what we're going to add. This large chain here, so adding this carbon group to our more substituted position. All right. Amine formation, so amine just gonna replace that VR. And then lastly, we are making an aldehyde, so as our hindered version of LAH, it's just going to do a single reduction. To give us our final product. That should not be a wedge. That just kind of looks like one, just a regular line there. There we go. Okay, this page seems a little easier than the fall one. We'll go through a lot of these Clasons and aldols in recitation today to kind of solidify that concept for you guys. Overall, this one looks a little easier to me. All right. You can do this a few different ways. Let's do it the other way. So if we add in Na, oh, come on. Sodium azide, NaN3. And then LAH. Can get us down to here. Let's see. Probably want to make an acid chloride. We need to add some carbons to this. I don't know why we have a 1 and a 2 in this box. So you get SOCl2, followed by your cuprate. And then adding in H plus and the amine. Should get you your final product. Okay, we have a acetoacetic acid synthesis. So we're going to add the 2 components of it, and then adding H3O plus is going to decarboxylate to get us to our final product. We talked about these yesterday. So adding in NaOMe. Let's do the methyl part first. So methyl iodide. We can do this again. So NaOMe followed by this other half of it. And then finally, H3O plus is going to let us do the decarboxylation step. So after our first 4 steps, we'd make and then adding in H3O plus is going to let us decarboxylate this portion of it to our final product. We're going to do a Robinson annulation, so adding an NaOH. I don't know how we're missing this carbon here. I think that was actually a typo. I remember telling people to draw that one in. Heat's going to be our last step here. And then last step, LAH, water. A little bit straightforward. I think at the end, if we have a little bit of time, we'll talk through these malonic acid and acetoacetic acid synthesis one more time, just to give you guys a little bit of a review on them. Although I think the next synthesis problem might be on one of them. Nope, wrong thing. Yep, okay, this is a malonic acid synthesis here. So we need to add both of these weird looking components. So if we throw in, so in our final product, this one's a little tough to see. This portion of it is going to come from here through a malonic acid synthesis. So let's kind of chunk through this. We can add these 2 giant components to it. So if we add in Na isopropyl here, followed by one of these. We could add the other half. If we add an H3O plus, We're going to decarboxylate one of these, turn the other one to a carboxylic acid. And then from carboxylic acid to a nitrile, we need SOCl2, ammonia, that gives us aramid. And then SOCl2 again. Goes to our final product. I want to say a lot of people didn't pick this one. Our other one, I think is more scary than it or less scary than it looks. So if we add in base, we can eliminate these. Oh yeah, that's what this was. This one was very similar to something we did on like I gave a bunch of practice problems for these. Adding in base. And then ozone. We need a methyl group here. So NaH. Methyl iodide. We want to do some sort of Robinson annulation. We're going to want a bunch of extra carbons. So our normal Michael acceptor is here. We need 2 more carbons on this side and 2 more carbons on this side. From this point, yeah, this is tough. We could do a cuprate addition, add these methyls in. An ether synthesis, and then H2. So adding an NaH, methyl iodide makes our ethers, and then we could add an H2 and platinum to get rid of that last double bond. Which reminds me, I think I need to post those extra synthesis problems. All right, let's take a look at the mechanisms, because that was brutal. Give you guys 1 more minute to finish writing these down.
Excuse me, I just have one quick question.
Yep.
Are you gonna drop the lowest exam or are you gonna take the average?
Gonna drop the lowest exam.
Okay.
So
Oh.
I will post your guys's, they're not final grades, but they're like final grades up till now. So that'll be the lowest grade you can get in the class. And then if you choose to take the exam 4, it can only help you.
Okay, so whatever you have now, even if you don't take the other one, that's what you will end up with. That's correct?
Yep. That is the lowest grade you can get in the class.
Okay, thank you.
All right, let's do these last two mechanisms. Yeah, because this exam is mean, it feels like. Especially in a 5-week course. Yeah, over here. Okay. Can't attack this thionyl-chloride. From here, we are going to pull off a proton. Form our nitrile, make our SO2, kick out this Cl. Deprotonate with that last Cl in order to make our final product. All right, last one here. We've got a ketone and an aldehyde. The ketone is more acidic. We're going to pull off this proton. We can do an aldol addition first. We're going to make a 1, 2, 3, 4, 5-membered ring. We'll protonate with water. And then in our last step, because we're in heat, we can pull off proton, eliminate this water. To give us our aldol product. All right, that is everything you guys are going to see on this exam. If you guys have any questions, happy to take them. If not, we will do a bunch more of these aldols and clasons in recitation today to kind of help you guys get used to them. So if not, I will see you guys for tomorrow's exam.